In this video, we're going to jump into the chi-squared test of independence, one of the two which are classically thought of under the umbrella of a chi-squared test. So the way in which we look at this is we look at the two variables we're studying, the two categorical variables. And the reason this is called the test of independence is we're asking, are they independent of one another? Now, if you remember back to your previous stats course, the definition of independence is that one doesn't affect the other. So what we're really looking for is, are the distributions of counts within each column affected by the rows, and are the distributions of counts within each row affected by the column? So we'd expect for higher count columns to have more numbers in the cells than lower count columns, so that's okay. What we would not expect, though, is for some rows across the board to have a higher proportion of the values in it. So because you can think about this in terms of proportion, this is actually exactly what we talked about with our test of proportions in the previous video within this lecture. The difference is with proportions, we only had two rows. We had yes and no. But with the test of independence, you could have 2 rows, you could have 3 rows, you could have 100 rows. You could have as many rows as you wanted to. That is, you could have as many levels of that variable as you wanted to. Same thing with columns. Columns is not limited to 2 or 3. You could have as many levels as you want. Now, the trick is, if you do too many, your test isn't particularly meaningful. At about, it depends on the situation, but for a rough rule of thumb, maybe 8 or 10, you may consider, is there a way that this is actually considered continuous or something more? You may also consider questions like, is this meaningful? And what will I do with the answer if it comes out, quote unquote, statistically significant? You also need a larger sample size. But if you have these things, again, the flexibility of the chi-squared is pretty cool, and the test of independence is one of the main uses of the chi-squared. So because we're looking at if the rows and columns are independent, the null hypothesis is literally, is the column variable independent of the row variable? And the alternative is the opposite. Are they not independent? Does the row affect the column or the column affect the row? Now, I'll tend to say row affect columns here, but this is not directional. That is, we're not assuming a causal direction with this statistic. We're just looking at, does one affect the other or correlate with an effect on the other? Are they related to each other is another way to ask this. The null hypothesis says no relationship between the two categorical variables. The alternative says yes, there is a relationship between the categorical variables. But it doesn't say what direction the relationship goes. That is, it doesn't say it's the row that affects the column, or it's the column that affects the row. It's your experimental design that would have to be designed in order to make such claims. All right, so we take a random sample, and then we record the frequency for each cell on the contingency table. So there's 2 ways you can do data here, like if you're hand entering it. First, you can have a row as a participant, and then you'll have the row variable and column variable as 2 columns. And again, it sounds weird to say the row variable is a column, but think about categorical variable 1 as 1 column and categorical variable 2 as a second column. So think about the favorite marketing advertisement. So I've got 3 ads, 1, 2, and 3. And then think about your favorite marketing method of delivery. Like, do I prefer paper? Do I prefer email? Do I prefer mass marketing versus individualized marketing? That kind of a thing. So I've got 2 categorical variables as columns, and then for person 1, I'd say, well, did you prefer add 1, 2, or 3? And they'd check one of the boxes, so add 2 maybe. And then they would also say which kind they preferred. I preferred email to in paper. And then I would go out and ask another person, and another person, and another person, and another person. So what's interesting about this type of design is you could actually have 0 people say they preferred email, or 0 people say they preferred snail mail. It's not a requirement to have all of these cells full by the sampling method. Now, for the design, we do want to make sure the expectation of every cell is above, say, 5 or something like that. But it's not a requirement of the design. In fact, it could happen that some of your cells are empty. All right, so we have our random sample. We asked them about the 2 categorical variables, which we're going to put in rows and columns. The second way you could organize your data is just to make that table that we looked at in the previous video, the first video on this lecture, and just draw out that table with all the levels of one factor as the rows and all the levels of the other factors as the columns, and then just use like tally marks within the table in the appropriate cell as somebody tells you that this is the cell they fall into. All right, and then from there, we do exactly what we did before. We compute the expected value within each of the cells. We do the observed minus the expected squared over the expected and add all those up. And we compare to a chi-squared. So this is the exact same setup. Now, the thing is as we discussed in that previous video, we don't have the k minus 1 degrees of freedom that the book had us saying, or the notes. We actually have the number of rows minus 1 times the number of columns minus 1. So if I've got, let's say, 4 columns and 3 rows, I would have 1, 2, 3 minus 1, so 2 degrees of freedom on the row side, 1, 2, 3, 4 minus 1, 3 on the column side, and I'd do 2 times 3 to give me 6 total degrees of freedom. So we're going to keep looking at these homes, and we want to see, is the price of the home independent from the type of home that it is? Now, I will say, first of all, that if I'm looking at this type of data, because price is a continuous variable, I would probably rather use an ANOVA to look at the data where I've got a categorical variable and a continuous variable, and I'm looking for the relationship between those. Or maybe some kind of multinomial logistic regression if you wanted to do something very fancy. But no, this is definitely going to be an ANOVA if I were looking at it like that. But sometimes, and this actually happens bizarrely frequently, I don't have access to the raw data. I don't have access to the number. All I have that's publicly available is, was the house sold for less than $200,000 or more than $200,000? And I know that you actually can find more detailed data on this that is publicly available. But for the sake of argument, we'll just say this is all that was publicly available, and that's why we have to break it into groups. Also, this illustrates that even if I had the raw numerical data, I could still break it into these groups. Notice that I can't do the reverse. I can't start from the groups and then break it into raw numerical data. That is, I can't tell you it's less than $200,000 and then you tell me, oh yeah, that's $156,800 that it sold for. But I can have you say it's $156,800 and then go to, oh yeah, that's less than 200,000. So this direction only moves one way. You can only go to fewer categories. You can't go from fewer categories to more categories. In any case, we're breaking this down and we're looking to see, is there a relationship between the cost of the home and the type of home that it is? In this case, the null hypothesis, and this is important, this is true for the proportions too. The null hypothesis is that these don't affect one another. And in this case, we tend to think, because it doesn't make sense that the cost, like I see that it costs this amount of money, and so that's going to change the type of home that it is. We would tend to think in the opposite direction. Okay, well the type of home that it is influences the cost. So in this case, we would say that the type of home doesn't influence the cost, and then the alternative hypothesis would say that the type of home does influence the cost. Or these are independent from one another, they're unrelated, no relationship between type of home and cost, and that they are not independent. There is a relationship between the two. So we do have 4 columns here. We have 2 rows. Doing 2 minus 1 times 4 minus 1 in my magic box gives me 3 degrees of freedom. I look at my chi-squared cutoff for that as 7.815. For my alpha of 0.05, and so I'll compare P to alpha of 0.05 and my test statistic to my cutoff. So calculating my test statistic real quick, I see my test statistic turns out to be Remember, this is observed minus expected squared divided by expected. Remember, expected is just the row total times the column total divided by the total sample size. After running through that, observed minus expected squared over expected, adding all those up, I get a test statistic of 9.149. And so we're seeing if that is bigger than my cutoff of 7.8. In this case, yes, that is bigger, and because it's bigger, we reject the null hypothesis in favor of the alternative. That is, we reject that these are independent in favor of, or we now believe that they are not independent, that there is a relationship between the type of home and the cost. And again, because it doesn't really make sense to say cost affects types of home, we would say that the type of home probably does have an effect on the cost. But note that that direction does not come from the statistic. That direction of interpretation comes from the design of the study, specifically from the idea that one of the variables does not sensibly influence the other one. For the p-value, I'll just ignore this table approach. I mean, you always can look it up this way. The p-value is between 0.05 and 0.025, but we'll just use R to calculate. The p-value in this case is 0.0274. So for that p-value, it's less than 0.05, so we reject the null hypothesis and come to the same conclusion. Again, p-values and test statistics, as long as you're using the same alpha, will always come to the same statistical decision. And this is the critical value approach that we've discussed previously. So we'll stop here for the test of independence. This has been talking through the chi-square test of independence, which is comparing two variables to one another that are both categorical variables. We discussed how we can categorize continuous variables to be included in this type of analysis, the formulas for this, and how we interpret the results. In the next video, we'll discuss the goodness of fit test, which is the other main way in which we use a chi-squared test.